What we want to do is begin with our next presentation, which is coming from Adria Carbo. And Adria is a PhD student, nearly completed, in our interdisciplinary PhD program in genetics, bioinformatics, and computational biology, or GBCB as we call it here. And I'll probably be mentioning it more than once, and I'll even have some little flyers out asking you to perhaps take them back to your universities and so on as we try to bring more good students to Virginia Tech as part of this program. When I say he's nearly completed, his defense is next Monday, so when we with that said, if any of you have any questions you think ought to be asked at his defense, I'm on his committee, Joseph's his chair, so we can certainly ask those questions. Something really hard would be good. So he is working with Joseph Riera. He's part of the MIEP program, and in the NIML lab, you'll see a lot of these, another abbreviation, Nutritional Immunology and Molecular Medicine Laboratory. Adri comes to us from Spain. He got his BS in biotechnology from the Universitat de Vic. And first came to Virginia Tech working with Joseph as an undergraduate intern, and then he returned for graduate study in the GBCB program. He really exemplifies the goals of what we try to accomplish in GBCB, where we have people with expertise in both experimental methods and in computational methods. And you'll see that as a result of this talk. And one other thing I'd like to mention, I think I introduced him once before for a seminar perhaps, he's also a bit of an entrepreneur, in that while he was a student in Spain, he formed a company called Carpe U, something like this, in Barcelona. And it was designed to promote nightlife in Barcelona. But I think he's probably...
I think it's already very promoted.
But I think he missed an opportunity in not trying to do the same thing here in Blacksburg. In any case, the title of his talk is, it's different than what I have here. So, PPAR gamma activation drives Th17 cells into a Treg phenotype.
Thank you. Well, thanks everyone. Today I'll be giving you an exact example. This morning Dave gave an introduction on how computational modeling works. Ken gave an overview of CD4 T cells. And now what I will show you here is how we can get from an experimental view on CD4 T cell differentiation and how we can compute and simulate a model in order to generate predictions and within the context of CD4 T cell differentiation. And before I start, let me tell you one thing. When I started my PhD, and I consider myself an immunologist, when I started I had no idea about computational immunology. Actually, I jump-started my PhD by going to a summer school for a workshop that was very similar to this. And the reason why I'm saying that is because we talk about computational modeling and immunoinformatics in conferences. Everyone is so scared about models and differential equations. And there are ways, the ways that I'm going to show you today, where you can use a very user-friendly piece of software such as Copasi that will work the math for you, and then you can just focus on the immunology, which is what you have expertise on. So let me jump into the presentation. Ken showed you this cycle here, and this is what I will be going over today. What we do within the Modeling Immunity to Enteric Pathogen Center, one of the modeling approaches we have is first, we go to the literature, we do literature mining, we also have some in-house generated data, and with all this information, what we do is we create a network. And this afternoon, we will teach you guys how to create these networks. Once we create this network with Cell Designer, what we do is we implement this network into modeling software. And in this case, we implemented the network into Copasi. And again, all these processes will be taught to you this afternoon. Once you figure out the parameters and everything in Copasi, what we do is we start running in silico experimentation. So computational simulations, scans, time courses, in silico knockout. And the reason we do this is to generate novel predictions. And once we have these novel predictions, what we do is go back to the lab and run in vitro and in vivo animal models, and in vivo can be with mice models. We've run validation studies with pig models. We also have some human stuff going on. And then what we can do is go to that prediction, test it in the lab, and validate and say, yes, this works. And then of course, once we have this data, this is available data that we can plug back into the models. So it's a natural cycle that we've been following, and this is our modeling approach. So today, with this presentation, my goal is to walk you through these processes so you understand how we do the modeling here. All right, this is a little bit of outline. I'll give you some background introduction, and I'm going to go really fast. I just have 1 or 2 slides on CD4, but can't have any tremendous introduction on CD4, so I'll go by that very quick. I'll introduce you to the CD4 T-cell computational model. We'll talk a little bit of model calibration, and I'm going to link that to some of the activities that we'll be running in the afternoon. I'll show you the in silico experimentation that we run and how we set up our strategies to find these novel hypotheses. And then I'll show you what we did to experimentally validate the hypothesis that we came up to. And then some conclusions at the end. All right. As immunologists, you know the immune system is characterized by 2 big responses, adaptive and innate immune response. The innate immune response, I want to highlight that is very non-specific. So we have these macrophages, these dendritic cells and neutrophils, one of the first barriers of immune response. Secondly, we have the adaptive immune response, which is more specific. CD8 T cells, B cells, and then our object of study, which is CD4 T cells, which, as you may know, orchestrate adaptive and also the immune response by secreting these factors, these cytokines, and other soluble factors in the environment. So the CD4 T cell differentiation and development, or in other words, for a CD4 T cell to be fully differentiated, it needs 3 different signals, as you may know. First, it needs a TCR engagement with the TCR receptor. It needs a co-stimulatory signal. It is usually mediated by CD28. But also, it needs a cytokine signaling. So the CD4 T cells have various receptors for numerous cytokines. And cytokine signaling needs to happen for a CD4 and a CD4 T cell decide where am I going to go, what I'm going to differentiate to. In this model, the CD4 T cell model focuses on cytokine signaling. So as you can see here, CD4 T cell differentiation is quite a complex process. We have a naive CD4 T cell, as Ken was saying, depending on the cytokine milieu or how the environment is composed of which cytokines, this naive CD4 T cell will differentiate into different phenotypes. And of course, each phenotype has different functions and also has its landmark transcription factors that will be expressed. As Ken was saying, a naive T cell that encounters IL-12, 15, or interferon gamma in the environment will differentiate into Th1, express specific transcription factors such as T-beta or STAT1, and then secrete interferon gamma. This presentation will be focused on Th17, which is induced by IL-6 and TGF-beta, expresses ROR gamma T and secretes IL-17. And I want to highlight in here, it's induced by TGF-beta, secretes also TGF-beta and other anti-inflammatory cytokines such as IL-10, and expresses FOXP3. Now the CD4 T cell, as I was saying, this process is complex. It's not only an activator pathway type of process, also other cytokines that are in the environment will inhibit different pathways. So it's quite a complicated process. And also there are some other transcription factors that they are not part of a specific phenotype, but they are in CD4 T cells. An example, PPAR gamma, and I'll be talking about PPAR gamma now, that can mediate the plasticity of different phenotypes. All right, so let's jump into the CD4 T cell computational model. This is the network. I don't know if you can see this here, but this is the network that we created showing CD4 T cell differentiation. And this network represents 4 different phenotypes. We have our Th1 right here, our Th2 pathways right here. We also have our Th17 pathways in the upper right. And last, we have our Treg, as copied. The way this model works works, and you'll be playing with this model in the afternoon. See these external cytokines here? With this model, we are able to initialize the model in different ways. For example, if we set up our initial concentrations with IL-6 and TGF-beta and no other cytokine, the model will activate the Th17 related pathways. If we change the cytokine environment, for example, if we just put TGF-beta right here and IL-2, the model will differentiate into one active. So this afternoon we'll show you in more detail how to play with this model. Just to give you an overview of the model, it has 93 species and 52 reactions, which is considered a big comprehensive model. And these are how the ODEs look like. And as I said, yes? Yes. Oh, good question. So if we go back, I'll show it to you here. All right, you see, for example, here, this would be our IL-10 activation. The IL-10 receptor, when it binds the IL-10 external cytokine, this connection here, this is a reaction. So I'll be calling these nodes species, and these will be the reactions. So for instance, if A goes to B, the way these two proteins are linked is by a reaction. And I'll be talking a lot about the reactions in a minute. ODE. This is, for example, the ODE that calculates the differential expression of external interferon gamma in this model over time. And I didn't write this. This was generated by Copasi. And all the models that you will look with Copasi, all these ODEs will be generated for you. You don't need to worry about that. And I'm not planning on you guys reading this, but just so you have an idea, these are all the equations together of this model. So it's a big model. Going back, Milton, to your question. When we have a node A that goes to B, this is linked by the reaction, as I was saying. But how fast is that reaction going? Or is it very fast? Is it in a slowly fashion? Is it holding on to B? Is it holding on to A? The way we have to dynamize these reactions is by setting up specific parameters in these reactions. A more specific example of the model, we have our external interferon gamma binding to the receptor of interferon gamma, and this will create an interferon gamma membrane complex. Now, this equation is governed by different parameters. The more parameters, the more complex your function, your reaction is. And you may have the question now, okay, that's great, we created a model, we created a network, but how do I choose which value should I give to these parameters? There are so many. I have no idea if it should be 0.1 or 1 times to the 6, we don't know. Luckily, we have a process named pyramid estimation that will help us with experimental data to set up all these values. Because at the end of the day, we need to adjust the dynamics of the model. A model without dynamics is just a static picture. There's nothing going on. So how do we do this with Copasi? Again, this is something you'll be learning this afternoon. We have our experimental data or in-house generated data, and we put this data all together in a calibration database. Okay? You will be taught how to put together this calibration database later today. And what we do with this calibration database is we import this experimental data into Copasi, and Copasi will run an algorithm that will set up all these values. And this process is called parameter estimation. So pretty much what you need to calibrate and specify your models is just your experimental data. Copasi will do the job for you. Once we have the results, they will look like this. And let me explain to you this figure here. This calibration, this example here comes from a 4-experiment calibration database. 0, 1, 2, and 3, these 4 experiments. Now, this was data that we took from a paper from Betelli, a Nature paper that describes the crosstalk between Th17 and Treg. And they run 4 different experiments. The first one were cells only stimulated with TGF-beta. The second one were cells stimulated with IL-6. The third one were cells stimulated with both TGF-beta and IL-6, and the last one was an unstimulated culture. And what we can see here, these values here in the top, the red, blue, and you can don't worry about these two ones. The red and blue are for FOXP3, the light blue and the purple are for IL-17. This right in here is the measured value, is the experimental value, the value that you give to capacity with your calibration database. And here with TGF-beta, you can see how experimental value falls in the hundreds. Capacity, this blue value here, capacity is able to fit this point. So what capacity is doing here is tweaking all these parameters in the model, running this algorithm, and then it will say, okay, I was able to fit this experimental data here. So do you see how these 2 points are very close together? And same for these two, same for these two, same for these two. What happens with IL-17, for example? When we have IL-17, the measured value is up here. The fitted value is together with it. So this is an example of how a good Premier estimation results. Yes.
Sorry, I missed. What are the X and Y axis again? Are these scores, or what do you mean by those parameters?
This y-axis would be the concentration of the model, and this x-axis, capacity by default, which is the x-axis, but this just represents the first experiment, the second, the third, and the fourth. Yeah.
Give us an example of a real experiment, a vitro experiment.
Sure.
And this is by now, how many cells, for how long, how do you set up this so you can think of capacity?
If I remember correctly, what Natalia and all did here was run an individual cultures with TF17, and then she measured IL-17 and FOXP3. Depending on the data you need for calibration, the reason why we decided to use this paper was because it gave us, our story was, or is, we have an induction of a CD4 T cell, and then we measure what happens in the intracellular compartment, which is exactly what she did here. I used these cells differently, and then I measured what happens in the intracellular compartment. So this was a really good fit for our model. But you can choose, depending on the model you want to create, you will need to choose which kinds of data you want to use for calibration purposes.
So another thing, so going back into this parameter, so you're talking about a deterministic model. It's not a stochastic model.
Sure.
So basically, you're assuming that the data that you're taking from the experiments are inherently Gaussian and is the high determinant, because these processes are expected to be stochastic in some or
Sure.
the parameter working.
So there are two ways you can incorporate variability. The first one is, and I'm not going to show you in this presentation, but I'll show you guys later this afternoon or tomorrow as well. We have tools that will run our deterministic model and tools that apply stochasticity to those deterministic models. So with that, you can check the variability of your simulations. The second way you can account for variability within the ODE scenario is these calibration databases. You can have different replicates. For example, this measure value of FOXP3 may be composed of 3 different replicates, and Copasi will calculate the average of these 3. So you can account for variability for that. Yeah. Corey?
Will we learn what the fitting algorithms are this spring?
You will learn.
Can you repeat that question?
Yeah, Corey was asking if we will learn how to run these algorithms in the afternoon.
No, not how to run what algorithms you're actually using if we know the math side.
Okay, so which algorithms we will use, the different kinds we have? Yes, we will. Yeah.
So a question is like when you say the model estimation, you estimated the parameter only, or you also estimated the form of the equation?
So the question is, do you estimate your parameter values, or you're also guiding which function you should use for that specific reaction? For Premier estimation, we just estimate the parameters. Now, if you see that your Premier estimation hasn't worked, you can pinpoint and map back to your model and see what is not working. And maybe one of the things that's not working is that you're using a mass action function when you should be using a Hill function or another type of distribution.
Slightly going back a bit,
but I want to go back to establishing your initial network.
Mhm.
This was also done solely on literature mining and your in-house data, or did you again use some kind of algorithm, or what led you to establishing first this network of parameters and now an algorithm?
That's a really good question. You have different options to create your network. In this case, this network was created solely with literature data and also our in-house generated data. Now, we will be showing again in the summer school ways, for example, you can make sense if you start getting pieces of different papers on the literature. Now, what happens if you have a sequencing data set? Well, there's a ton of data in there. We have ways to get the sequencing data set, and this is something we'll be showing you on Wednesday, and infer a network out of it. So there are algorithms that run for network inference as well. Ishmael?
So I'm very new to this field. So I was wondering that once you got this picture for parameter estimation, how do you apply this graph to the model you showed in the previous slide?
That's a good question.
How does it relate?
Shivani is asking how you can apply these results into the actual model. So how you move from results into the parameters of the model. This is as easy as clicking one button in capacity. So at the end of the Premier estimation, there will, and I'll show you this after. There is a place where it says update your model. You just click in there, and all the results of the Premier estimation will just move to your actual model. So it's working, literally. Okay. Yes.
Okay, that's good to know. Thank you.
All right, great. Something we want to do once we run our Premier estimation is, well, we've set up all these parameters, but now we want to check if it's really working. So one of the things we did with this model is, based on the central differentiation dogma that we have in here, we initialized the model with different cytokines, and then we made sure that the model was upregulating the nodes or the proteins that was supposed to upregulate, and was also keeping downregulated other phenotypes related molecules. So to give you an example, after calibration, we initialized the model with just TGF-beta, and then we just made sure that the model is producing FOXP3, but it's not producing interferon gamma, for example. So it's kind of like our quality control for the model. And this is the result of the quality control. And once we check that everything is good to go, then we stem quality control, and at this point is when we can start running our in silico or computational experimentation. Yes, Ron?
One point on these graphs, the dashed lines are the predictions of the model. What is the prediction? What is the value?
In this case, this is a result of a time course simulation, so everything you see in here is computational.
Okay.
The reason why I use dashed lines is because I had so many species in here for so many nodes that I wanted to use dashed lines just so you can detect that one.
So all of this is simulated that you just want to make sure that the simulation makes sense.
That is correct. All right. The first node that we wanted to check in this CD4 T-cell model was the peroxisome proliferator activated receptor gamma. Now, PPAR gamma is a nuclear receptor and transcription factor that has been known to modulate some aspects of CD4 T-cell differentiation. For example, the loss of PPAR gamma results in enhanced antigen-specific proliferation and overproduction of interferon gamma. No PPAR gamma, interferon gamma is going out the roof in CD4 T-cells. PPAR gamma inhibits the Th1 and Th17 programs in experimental allergic encephalomyelitis. Also, it was found how PPAR gamma inhibits more specifically Th17 when it's been induced with IL-6 and TGF-beta, and it uses ROR gamma T. And then on the other side, we have how PPAR gamma promotes anti-inflammatory responses. And I'm showing you PPAR gamma here. And this brings me back to one of the questions that was done earlier this morning, where you were saying, well, you have a big model, but what if you're only interested in this small one? So this is an example. We have a very big comprehensive model that allows us to work with a lot of flexibility because we can check a lot of things. But we can check what happens with this specific model in response to these other number of molecules here. So the first thing we wanted to check with p-bar gamma computationally is, well, does the activation of p-bar gamma influences the differentiation or the state of a CD4 T cell? And we focused on Th17. So we have an A T cell that we use with IL-6 and TGF-beta. It will differentiate into a Th17. And what we did was we run a scan. Now you may have a question, okay, what is a scan? Scan is a specific task of Copasi that evaluates, that scans a concentration of a node you specify, and then that's represented in the x-axis, and then in the y-axis you can check the concentration of different molecules of your model. What we saw with this specific simulation is that if we initialize the model to a Th17, so we have RYK-T and IL-17, but we give increasing concentrations of p-bar gamma, these Th17 related molecules in a single cell environment will go down, and then FOXP3 will go up. So this was kind of our first hint to say, well, is this Th17 being plastic and differentiating back into a Treg? So that was our first hint. And we continued, this is the explanation of the scan. And we continued with the computational simulations. The next one was to check what would happen if you have a model that's a fully differentiated Th17, and at some point during the lifespan of this Th17, p-bar gamma gets activated. What will happen? So for that, we initialize the model into a Th17, and then we run a time course. And then at some point in the time course, we created an event, and an event is an action that you are telling the model to activate at some specific time, and we'll get into that this afternoon as well. But at some specific time, we said, okay, now activate p-bar gamma. And what's going to happen to the model? And what we observed is that these Th17 related molecules went down, and this FOXP3 went up. So again, we're seeing how a Th17, once p-bar gamma gets activated, just downregulates the Th17 machinery and upregulates the Tregs. Yes, Osric?
So I guess I'm a little lost. What is this simulation based on? So you showed us our initial data set you're talking about paper, but what is this simulation supposed to do? So what data is usually to develop these strategies?
So the question that Osric is asking is, what data is the model using to produce these results? I've just shown you a very small part of the calibration result, but there's actually a huge database behind this model. To calibrate this model, we had to break the parameter estimations into different ones and calibrate different parts and generate and also gather a lot of data. So everything that the model represents is based on experimental data that we've used for parameter estimation.
So is this all in vivo data that your parameter estimation is based on? Or is it from different?
This result is a result of different data sets that we've used for P, or parameter estimation.
From same species?
Or from different species. One of the items, and that's a good point, one of the items that computational modeling offers is that you can have mouse data and pig data, for example, and if you need to calibrate your model, you can use both data, account for this variability, and also assume that your model may represent two different species. It would be great, for example, if we have an IPA data set and we have all this data coming from the same source. That reduces our variability in a greatly manner. But sometimes, for instance, with this model, we had the need to gather data from different places, and therefore we need to assume that this may be happening in different species.
So after you have estimated the parameters, do you perform a model validation of these different components?
Yes, and I'll be showing you. Yes, Shivani?
So, since you said that all this model is based on experimental data, so where does your hypothesis come from?
I'll exactly show you that. So what Shivani is asking is, if you are calibrating your model with all this data, isn't your model going to show you all this data? And the answer is, there are two data sets for modeling. The first one is for calibration. Once you have your calibration, you're going to run your in-silico experimentation. And then with in-silico experimentation, you can play like this. You can say, in a single cell scenario, what happens if I upregulate PPAR gamma? Well, we're seeing how this cell is switching from Th17 to Treg. But for instance, the data that we used to calibrate PPAR gamma was just telling us, one paper was just telling us it just inhibits RY-gamma-T, but not in a single cell scenario. So what the model is giving you is this extra power of predictability where you can put all these pieces together from different publications and then see the big picture and see what's happening in just one cell.
So did you have PPAR gamma in your model originally that you showed us, or did you set it up based on basic T-cell differentiation and then add it in as an experimental question?
So Claire is asking if we added PPAR gamma when we were setting up the model, or if it was added a posteriori. We added PPAR gamma when we were constructing the model because we were interested in PPAR gamma as well.
So your starting point in the model is based on the initial conditions you set for the cytokine levels or the T cell initial values.
Yes.
It doesn't have any antigen presentation or anything before that.
So what she's asking is if our T cell model accounts for TCR activation. The answer is no, we don't have TCR. We don't have the TCR node because we're just modeling cytokine signaling.
But if you want to do that, does Copasi have that
Yes.
capability?
You would be able to download this model, add the TCR related pathways, connect them, recalibrate, and use the model. Yes.
Can you generate these models in a specific manner? Let's say you activate PPAR gamma in DCs and you want to look at the effect of that in T cells. Can you do that?
Yes. The question that he's bringing up is a really good question. Is what happens if you intracellularly activate PPAR gamma in a cell type like the dendritic cell? Can you check what happens on the other side of the T cell? Yes. This model cannot do that. This is part of a multi-scale model. So you're now talking about what happens intracellularly and what happens at a cell-to-cell interaction level. We'll be talking about multi-scale and showing you some examples on Thursday. Yeah. All right. The third experimentation, computational experiment that we run was a combination of a time course and a scan. And what's hanging here is maybe a little bit confusing. So here we have time on the x-axis and concentration on the y-axis. Now, each different line is an increased concentration of PPAR gamma. So this is mixing our first scan with our time course, all right? So let's give an example, for example, here on FOXP3. When PPAR gamma, and this is initialized on a Th17. So a Th17 with 0 PPAR gamma, the FOXP3 is right here on this line, right here, this first line. The next line will have an increased concentration of PPAR gamma at a specific interval. So this will be the next line. And then the next, the next, the next, the next, the next line, as we increase the PPAR gamma concentration. So what this is telling us is, in a timely, or it's time dependent, the fact that we are increasing PPAR gamma and then FOXP3 is going up as these Th17 related molecules are going down. So this is a mix, it's another strategy that you can use in Copasi. And again, we'll show you how to do these things this afternoon as well. So after running all these predictions, oh, I have one more. Yes, the knockout. All right. So one of the real cool things I think that you can do with computational models is that you can create specific knockouts of your model. And how you do that? Well, if you, for instance, downregulate the ability, or you ablate the ability of PPAR gamma to be activated, you are knocking out PPAR gamma in the system. And then you can get the system that's a PPAR gamma knockout and check what's happening with the system, with Th17, with Treg, etc. So that's what we did. We have our Th17 here, and this is our wild-type model, and this is a model where we ablated this ability of PPAR gamma to upregulate. And what we can see is how these Th17 related molecules are being upregulated. All right? Now, if we initialize the model to Treg by just putting TGF-beta in the environment. FOXP3 in the wild type is up here. When we knock out PPAR gamma, FOXP3 gets downregulated. So there's another option you can do with the model. So after all these predictions, the main hypothesis that we got generated from this model is, well, we have that activation of PPAR gamma in Th17 downregulates. So one is PPAR gamma triggers a change in phenotype from Th17 to Treg, clearly. Second, we have this loss of PPAR gamma with the knockouts. So PPAR gamma indeed modulates Th17 and Treg phase. And third, the increasing concentrations of PPAR gamma with the scan, this is telling us that PPAR gamma can exert its effect in a dose-dependent manner. So with that, we go back to the lab, and what we are testing, and these are the 3 different examples that I was mentioning to you. But as I was saying, with this, we go back to the lab with the main hypothesis that we want to test, which is, well, PPAR gamma activation drives Th17 cells into an anti-Treg phenotype. And we started setting up experiments. The first experiment we set up was an in vitro experimentation. We used wild-type mice and mice that lack PPAR gamma, specifically in CD4 T cells. And you may be very familiar with that. We isolated naive CD4 T cells, we enriched them, and then we cultured them under Th17 conditions for 60 hours. Once these cells were differentiated, we checked, let me show you here first this. Once these Th17 cells were differentiated, at that point, we checked ROR gamma T and IL-17 using flow cytometry. Also, at this point, what we do with the cells is treat them with increasing concentrations of pioglitazone, which is a PPAR gamma agonist. It activates and we also check, after some time, we also check the levels of ROR gamma T and IL-17. So what these results are telling us is, well, at this point, before starting the PPAR gamma or the pioglitazone treatment, we can see how the wild types have less ROR and IL-17 than the CD4 T-cell-specific PPAR gamma knockouts, which is exactly what we saw with our computational prediction, where we computed in silico PPAR gamma knockout. Also, we saw how with increasing concentrations of pioglitazone, or PPAR gamma activation, if you want to see it like that, ROR gamma T and IL-17 are being decreased. So ROR gamma T goes from 42 to 20, IL-17 goes from 11 to 5.19%. FOXP3 on the other side is being upregulated from 4 to 6.41. Of course, if we run, this is a computational prediction, which is in line with this. Increasing concentrations of PPAR gamma will downregulate Th17, will upregulate Treg. Yes, Martin.
Is pioglitazone able to rescue the normal and PPAR gamma T cells?
Ronan is asking if PPAR gamma was indeed turning this Th17 to Treg. What we're seeing here is a change in the transcriptional machinery. So we are seeing obvious Th17 cells are in fact turning into Tregs. And I'll show you one more piece in the in vivo experimentation where we saw how mice were getting better when we were upregulating the Tregs. Yes?
So you said that the model was a single T cell, right? And you're sending your initial concentrations. And obviously this is at the population level, and it makes sense that one T cell, if the levels are going down, the population level will follow. But do you also see the same thing if you actually model a whole population of T cells with the same model, but all starting maybe at slightly different concentration, following over time, seeing if you get the same effect?
Mm-hmm. So he is asking if we see similar results in population-based models. Something we've been working on is, and going back to the multi-scale, is having, for example, different entities of CD4 T cells where you can play with the intracellular compartment of each one, that what's going to be the cellular response to that. That goes back to a multi-scale problem.
Right.
And for instance, in this case, it is a single cell model. So this can help you delineate what's going on, but yes, ultimately, you may want to check that in a multi-scale model. But of course, it's way more complicated.
Just because it might not be, so it might be that at the single cell level, it's going down slightly in all the cells, but of course it might be some cells going off and other cells staying.
Sure.
So that's important.
Sure, and I agree with you. Another piece of information is when we validate our predictions, we just don't do just in vitro. We also validate our predictions using in vivo animal models, because also we believe that there are other factors that will account for these behaviors. Dendritic cells getting into place, including some other cytokines, macrophages going in 1 and 2. So that's why we also want to run the in vivo setting to confirm that this is actually happening when you have all these other factors that were mentioned. Yes?
From a compartmental modeling perspective, and with respect to kinetics or cell trafficking, which specific tissue does this represent? Like, is it the lymph nodes? What did you find the results to be compared?
So this would represent, and this is based on the data we use for calibration. To calibrate, we use data from effector sites and induction sites. So we assume that this behavior would happen in both effector sites, such as a colonic laminopropia or a gastric laminopropia, but also at induction sites, such as lymph nodes, spleen. Now, this will happen if the environment has all these cytokines. So to calibrate this model, we had to also look for data that was coming from both places.
So you do take into account the cell trafficking?
Not explicitly in the model, but with the in vivo experimentation, again, there's cell trafficking, and we were able to validate that as well.
Okay.
Yes?
So when you say, because you said this model is built on the single cell, and it might have the other factors from other cells. But so when you do the validation on your models, so when the new experiment coming out is different from your model prediction, so how you consider if this kind of difference is because of the model or is because of the new factor which you are not even considered?
So the question is, once you see the validation results in vivo, for example, with other factors, how do you distinguish that this is because of a single cell or because of a compounded effect of different factors? So with this model, we're able to determine the single cell effect, and we can validate that with in vivo. However, if your question is in regards to different factors that are coming into play and you want to distinguish these other factors, then you have to move to a multi-scale environment. Because with ODE, with a single cell model, you wouldn't be able to
No, say you use the new data, you can still feed your model to the data actually. You can just change the parameters, you will be another one. But you also can include a new factor which will make your model fit to all the data as well. So how you choose both? Like you choose either have a new factor or you just change your model.
So what you're saying is, why did we choose cytokine signaling if maybe other factors are affecting CD4 T cell differentiation? Okay, as modelers, there's never, and Stefan, you're gonna agree with me, the perfect model does not exist. You can have a very accurate model, but you will see that the more nodes and the more stuff you put in your model, the more complex calibration simulation processes are. At some point, when you develop your model, you have to stop and say, okay, now I'm going to test. And then once you have this validated model, you can continue. For example, one of the things that we're doing in the version 2 of the CD4 T cell model is adding other phenotypes, adding Th9, Th22. But you could also choose, I want to add a TCR, or I want to add the effect of dendritic cells, or I want to add trafficking of T cells, for example. Or you do that in another model, but yeah. Yes?
I think I heard the question a little differently. And let me try to ask the question that Bob asked. If your data doesn't validate, what is the problem? Is it the model? Or is it that your assumptions are wrong? Or, I mean, how do you know what the problem is in that case? We can get into a very easy cycle of just make the model fit, make the model fit. But maybe you're missing something key from your model. I mean, how do you know where the issue is?
That's a real exercise involving. What she's asking is if your validation studies are not in line with your predictions, then what you do. The approach that you need to use if your validation studies are pointing out to a complete different direction, this means that during your calibration process, some of the assumptions you made were wrong. For example, if we calibrated this model with just effector data, effector side data, and then we are seeing how this model is not validated, then maybe we did that assumption wrong. Maybe we need to expand and do like both effector and inductive sides of infection or immune response. When your validation is not in line, one of the things you could do is, now that you have a data set for validation, use that data set for back to calibration. And then refine your model, refine your parameters. Maybe you're missing nodes, maybe you're missing the cell trafficking. And it's just a matter of going through the cycle again and then coming up with new predictions. And we've had, I mean,
So this model has age, lifetime, or I think about 7 years.
I think like
The model is about 7 years old when we originally started. And at some point we were fitting the data to the network to see a refined version of it. And we couldn't fit the data. There was one particular region, I can more specifically tell you what it is, but we could not fit it. So we were looking at literature and to get more information about that part of the model. And we figured out that there's actually literature indicating that there might be another feedback. Adding the feedback loop into the model starting to fit. You do the same thing if you now have new experimental information. Because first you try, which contradicts your model, with that assumption. First you try to adjust your parameters. If that doesn't work, then you're going to look if you're missing something. And if you miss something, or you may come up with hypotheses. If there's no other experimental information, you come with hypotheses about other feedbacks, other interaction between the players. Once you add that, you try if you can fit it in. So the model is never finished. The model will evolve. And this model, yeah, as I said, has a life cycle of already 7 years.
We continue. We're running a little bit short on time. Of course, the cells that were coming from the CD4 specific PPAR-gamma knockouts did not show this behavior in here. And then we moved into in vivo experimentation. And that's part of the discussion that we were having on the in vivo setting. In this case, we used an adaptive transfer model. So we got cells from these wild types and also the CD4 specific PPAR-gamma. We enriched the CD4 compartment and we sorted CD45 RT high, CD25 negative, CD6012 high, and those would be our naive CD4 T cells. And we injected those cells, we transferred those cells into SCIP recipients. Now, SCIP recipients, I'm sure you know, they are immunosuppressed mice. They don't have any functional T cells. So everything that they receive is something you can assess and track and then measure. One of the things we saw is that by looking at the disease activity index, and this is based on a score from 0 to 4 based on how the mouse looks, how sick the mouse is, we could see how at the beginning of the experiment, mice were not sick, but then as days progress, this adaptive transfer model will spontaneously generate colitis, so inflammation in the colon. We could see how the CD4 transferred mice, the PPAR-gamma null transfer mice, were showing disease at earlier stage of the wild types. The wild types took almost 70 days to start showing some significant score in here. When we sacrifice this mouse, you can see this in here, the non-transfer mouse, the colon looks good. The mice that were transferred with wild-type cells, you can see how there's some loss of architecture here. We have some leukocyte infiltration that you can see here. Definitely a little bit of mucosal thickening. But then when we move to the PPAR-gamma CD4-specific knockouts, I mean, the difference is very obvious. The architecture is being completely disrupted. There's huge mucosal thickening, huge leukocytic infiltration. So what this is telling us is that at the tissue level, histopathologically, these mice are doing way, way worse. And we decided also to run flow cytometry. What we observed, similar to what we saw in vitro, is that these ROR and IL-17 in the PPAR gamma null mice, they have way more ROR and IL-17 than the wild type liver mice. What happened with FOXP3 is, and we checked the spleen, the MLN, and the LPL, and the differences are accentuated in LPL and MLN. FOXP3 was way downregulated in the PPAR gamma knockout CD4 specific transfer mice. Also in the LPL, we go from a 29% to a 12%. Which again, this is in line with our computational prediction. Our TH17s in the PPAR gamma knockout, we have more TH17, more ROR gamma T and IL-17. In the Treg onset, we have less FOXP3 in the knockout, which is exactly what we saw in the in vivo setting. We decided to run a second in vivo experiment, also with adoptive transfer. But in this case, and again, this goes back to a question of how you would set up your experimental validation. In this case, we wanted to validate, if you remember the time course, where at some point we activate PPAR gamma when TH17 is up, what would happen? This is what we tried to reproduce in here. So we have these mice that are transferred with just wild type, naive CD4 T cells. In this case, we use RAC2 to use a second model of spontaneous colitis. And these mice went all the way 68 days, and after 68 days, we euthanized the first set. And at this point, what we did was to see what are the levels of TH17, detect that we indeed have TH17 levels that we can treat. And at this point, from 14 days, we started the daily treatment with pioglitazone, an oral treatment to the mice at 70 milligrams per kilo. So every day I would go to the colony and treat the mice with pioglitazone, and we also had a placebo group with PBS. And the results I will show you focus on these 14 days, so you will see the differences. All right, the first thing we saw is that by looking at the disease activity index, of course, at day 0, after 68 days of transferring the cells, mice are pretty sick. When you start your treatment with pioglitazone, what you can see is how the non-transferred, of course, they have scores of 0. They are not sick at all. The PBS treated, they continue being sick, so they don't show any recovery at all. However, the mice that were treated with pioglitazone, not so much at the beginning, but by day 6 of treatment, they started getting better and looking way better as well. We also weighed the mice, and what we can see here is that, and before I comment on that, the adoptive transfer of colitis is a model where some mice will not lose a lot of weight, but they will not gain weight, so they will remain in this stable state until they are very sick and they decrease the weight very heavily. But what we can see here is that the mice that were treated with PDS, they were not recovering any of the weight, whereas the mice treated with pioglitazone recovered weight and were very, very similar to the mice that were non-transferred. This is a barcode for the histopathology that we took at the end of the treatment. And again, mice with pioglitazone, very reduced leukocytic infiltration, epithelial erosion, and mucosal thickening. So these mice were doing much better. And this was translated into the flow cytometry that we run. All right, this first row is the baseline, is before the treatment, the pioglitazone treatment, and then we have our PBS mice and our pioglitazone treated mice. And what we can see here is that if we check ROR and IL-17 in the lymph nodes, we can see how they go from a 16 and 19 to a 9 and 13. And FOXP3 is upregulated. So we are seeing again how when we activate this PPAR gamma, these mice are reducing the TH17 numbers, and they are promoting the Tregs. So they are turning these TH17 cells into the Tregs. And we observe a similar fashion in the LPLs, for example, with from 13 to 8 and from 14 to 6. And then from 3, we saw a big increase here with 14% for FOXP3 in the LPL. And this is in line with the time course plot, if you remember, where we activated PPAR gamma, and then we saw this TH17 going down, and this FOXP3 or Treg going down. So what we did with validation is we had our first hypothesis, activation of PPAR gamma in the TH17 cell downregulates ROR gamma T and IL-17 and upregulates FOXP3. And we validated that with this pharmacological activation of PPAR gamma using 5-glitazone that I will show you now, and also in the in vitro studies. Secondly, the loss of PPAR gamma impairs the ability of Tregs to express the FOXP3, but also accentuates the expression of TH17-related molecules. And we validated that with the PPAR gamma knockout experiments in vivo and in vitro using this strategy of the knockout. And last, the increasing concentrations of PPAR gamma led to increasing concentrations of FOXP3 and decreasing concentrations of TH17-related molecules such as ROR gamma T and IL-17. And we validated that with in vitro studies performing these increasing concentrations of PPAR gamma. So I want to go back to the first slide and show you what we've done. We got the data, we generated the network that I showed you. We implemented the network into Copasi, and we calibrated the network with experimental data, and that allowed us to run our in silico experimentation. And with that, we came up with this hypothesis, PPAR gamma. When PPAR gamma is activated, the TH17 cell will turn into a Treg. And we validated these hypotheses with in vitro and in vivo experiments. And then this data, what I was saying before, is that this data was used to go back to the model for next versions of the model to have a more refined model. So very good conclusions. We created a computational mathematical model of CD40 cell differentiation. This computational modeling predicted that PPAR gamma modulates the balance between TH17 and Treg, and also that our in vitro studies support this effect of dose dependency of PPAR gamma. The results of the adoptive transfer indicated that the activation of PPAR gamma by this oral administration of 5-glitazone favors the switch from TH17 to Treg, and that PPAR gamma is indeed implicated in the plasticity of this subset in vivo. The loss of PPAR gamma again favors TH17, impairs Treg. And last, and this is the point I always want to make at the end of this presentation, is we always try to have this translational value with the modeling. The models that you can create indeed can have a lot of translational value. For example, if you, in this case, we detected this node, PPAR gamma, and we observe how when you activate this node in the model, the TH17 is going to a Treg. Of course, these two phenotypes have opposite functions. One is pro-inflammatory, the other is anti-inflammatory. So for example, if you have a disease onset that's very highly characterized by the presence of TH17 cells, and indeed there are drugs that targeted PPAR gamma, if you can activate that, then you can ameliorate the symptoms of the patient. So I want you guys to keep in mind this translational value that you can also reach with this computational model. And with that, I'll take any other questions you may have. Yes.
So,
Thanks.
Can you explain how the output of the model, the information gained that the generator hypothesis was new or different compared to what you input the model? How did the model advance your hypothesis?
Yeah. So the studies that were published before were solely focused. Yes. What he's asking is, what was the novelty of the model? What the model added versus to what we calibrated. One of the good things that we could do with this model is to put pieces of a big puzzle together. So the previous papers, what they were pointing out is PPAR gamma inhibits TH17. That's the end of the story. Or PPAR gamma promotes STAT5 or TGF beta receptor. That's the end of the story. But we were the first, using this study, the first that we were linking, okay, yes, this is great, these pieces are good, but actually if we put these pieces together using the modeling approach, what we can check is that actually this happens in a single cell environment. Part of these papers were checking that, for instance, the inhibition of RORDMC, PPAR gamma can activate, or it can happen for other factors. But that was not checked on a single cell level. That's why we wanted to run this model.
If you go back to the previous slide in your presentation, so the first point you mentioned is that you successfully created a computational and mathematical model of the seed focus. Is that? I mean, I'm still a little lost out here as to like, what do you mean by a mathematical model in this case? Like, are you getting the analytical expression of the rate constants in some ways, or are you estimating them by solving these differential equations numerically? What exactly do you mean by mathematical in this case?
Okay, so the question is, what's the basis to say that we create a mathematical model? In how we analyze that math behind the model.
Was it analytical or was it numerical? Like, I would call, in my knowledge, I would call mathematical model some analytical expressions of those rate constants, and judging by the networks that you shown, like, look really complex to have some analytical expressions for it.
So another area, Copasi, and I'm telling you this with my perspective from an experimentalist or an immunologist. I don't have a background in that. But Copasi will create differential equations for you. And Copasi will integrate and will solve these equations. There are other tasks in Copasi, for example, sensitivity analysis, and maybe you said mechanometry here, that will work your math out to detect, for example, which nodes of the model are more critical in response to different initializations. So there are some tasks in Copasi where you can go deeper in the math and analyze some of that. In this case, for this simulation, we integrated this model using a LS integrator or something like that.
Yeah, I mean, obviously these are, like, you're solving these equations numerically, right?
Copasi.
Sure. Yeah, what Copasi is just calculation. But what I'm trying to understand is, like you showed in the very second slide, a complex rate constant, right? So how do we come up with that? Yeah, exactly. So is Copasi helping us with that, or at all, or is it like?
What does the right rate constant? Rate loss or kinetic function? It's a lot of this is intuition. There's actually literature around it. There are certain things which are fashionable over time, changing a lot of things. So there are log models. There are different things you can test it. And really every modeler has their preferred kind of rate loss they use. They are very generic, and in this case, well, we had inhibition or activation of reaction of what some of the processes. We choose a very simple on-off switch, basically kind of hill switch. It was sufficient for our model. There are many situations where that is not sufficient to come out with this. So this one looked complicated. It's complicated because it had a lot of things turning it on or off. And but the general form of the rate law was a generic one.
I think we're over time. We have time for one more.
I hate to cut off discussion. We need to start again at 1:30. We're going to need a different location. It might be a good idea to go ahead and break, because you'll have a lot of time this afternoon to interact with Adria, interact with Stefan, and really deal with some of the.
And if you have any other questions, I mean, we have a whole week ahead of us, so please feel free to reach me and I'll answer any other doubts.
One of the other comments I'd like to make is, as you think about this afternoon, keep in mind that your first model doesn't need to be this really complex.
That's actually a good point.
Talk a bit about
yes, the way this afternoon, the way we're gonna, because of course if we just throw this CD4 model at you guys with no capacity expertise, it will be kind of difficult. So we will have this kind of increasing approach. You guys will start creating a model that has 3 nodes, and with these 3 nodes, that will give you information on how to build this model. And then you're going to move from 3 nodes to a model that has 9 nodes, and then with these 9 nodes, you're going to run some in silico experimentation, and we'll show you how to do all these. And then, if you're done with these 9 nodes and you have more time, then there's another tutorial to reproduce everything that I've showed you here with the full CD4 piece of model.
So is this model available already?
Yes.
Okay.
And I'll show you this afternoon in the website. You guys can download this model and play with it.
Okay, so we're going to break for lunch. Now, take your stuff with you. We're going to be